from the standpoint if I was a student. Cool. So today I want to practice being resourceful and pulling things together out of the book. So we're going to practice using some key results, some that we haven't even talked about yet, but we will first, and then putting those into use. And then I want to have our first exam next week. So now hold on. Instead of an exam where there's problems to work, I think it would be really advantageous to have an exam where you just remember results and spit them out. Because knowing these theorems, like having them right there, that's essential for actually using them. So what do we think about this? So the exam 1 was supposed to be like at the end of chapter 4 or something. Well, that's, who knows when that's gonna be. I don't. It seems like a long way off. And we were gonna have 3 exams in the semester. And can you also imagine having an algebra problem to work cold on an exam in a 75-minute period, having multiple algebra problems, like show this, prove this? That sounds stressful and fraught with risk. In my mind, it's probably similar, right? So what I'm proposing is exam 1 is next week, and we'll talk about what day. We'll have a discussion about that. I'm not wed to any particular day. But I've got a list of definitions and theorems that would be on there. It would be a closed note exam, because what's the point?
Right.
You get your book out and copy it down for the exam, right? Yeah. So it would just be a matter of memorizing these key results, some of which you, thank you, oh yes, some of which you already know. What's a group? You might be like, oh shit, what is a group, right? But so I want to solidify those things. What is a cyclic group? What is a generator? So some of these just basic definitions and then some key results. Does this sound okay?
Yeah.
Yeah, I think it'll, and you'll know exactly what will be on there. And there might even be a part where it's like, give me some of these, because sometimes your mind just gets a little blank, even no matter how much you've remembered things. So, cool. So what I was thinking, we could do it Monday, just get it done with. Does that seem too soon? Because if we're not going to have like a review day for this, there's no point in that. So if we put it Wednesday, we would just keep moving forward in the material on Monday? Or would you just like to knock it out? And let me show you what's on it. Maybe that'll help make the decision.
Hello, Diana.
Oh, hey, Diana, good. Awesome, great day to be here. So Diana, we are talking about exam 1, which we're gonna have next week. And it's just gonna be memorize some definitions and theorem statements and spit them out without notes. No problem solving. Does that sound okay to you?
That's cool.
It seems cool, and I feel like it's useful. It's not just like some bullshit I'm making up to just have an exam. In some ways it kind of is, but it's also like super useful stuff. Okay, so right now we're pondering to have it Monday or Wednesday, and I'm going to put what would be on there, and then we can see how we feel about that. Okay, so exam 1, next, fill in the blank. So here's the definitions, and this will be closed note. So you'll just need to practice writing these over and over again. That's what I would do. If you're uncertain about how to study for an exam like this, I'm happy to sit down and chat with you about what I would do. So definitions, group, order of an element and a group. You already can probably do that, right? I mean, you've been using it like crazy. So some of these are going to be super easy, and that's the intent. I want some really low-hanging fruit on here. Oh, yay, everybody's here. Oh my God. Hell yes. So Trinity, so I'm saying this was like the 3rd time I've said it, but it's okay. It's all right. We're going to have exam 1 next week. It's just going to be definitions and theorem statements, no actual problems. Sound good? Sound okay? And so I'm putting up here, we're not quite sure what day yet. We're gonna decide as a group what works best for everybody. So group, order of an element or a group, subgroup. And to get these, I would just go look in the book at the official definitions they give. And if you get anything that relays, if like on the exam, you say something that's a little different, but it's got all the essential elements, awesome. That's great, bless you. It doesn't have to be word for word, it has to be content correct. Bless you again. Cyclic, subgroup, and then generator. A cyclic subgroup. And I think that's all the definitions. And you probably know all of these. This group one, you might be like, I need to refresh that, but you got it. You've been using it like all the whole semester. And then these are just theorem statements. Theorem statement, and there's like some corollaries. Not everything, it's the ones that I thought were most important. So the one-step subgroup test. The two-step subgroup test. If you know one of those, you almost know the other. It's just a slight perturbation away. Here's a good one that we haven't really hit on, but I think it will be useful from time to time, the finite subgroup test. We didn't talk about it, and it was just basically like if you have a finite set, subset of a group, when is it a subgroup? And it was like closure and inverses. I think that was it. Theorems for 1, for 2, for 3, for 4. So these are all cyclic subgroup theorems. And then corollary 2, oh wait, shit, of 4, 2. So of 4, 2, corollary 2 and 3. And I think it's 4, 3 is the corollary I'm looking for. Let's see, corollary. Let me check. These are all chapter 3 things. Well, except for definition. These theorems are. Oh, no, they're chapter 4 things. Duh, that kind of makes sense, right? So let's see. The next one's about Z. Let's see which one was it. Oh, one more definition. Sorry, Euler Fee Function, which you may already know. We'll talk about it today. Corollary 2 and 3, and then corollary of 4, 3 is, it's just called corollary subgroups of Zn. And it's on page 85. Corollary subgroups of Z mod n. A lot of these things look the same, especially once you know like theorem 4, 2, corollary 2 and 3 are just special cases of it, saying the same thing in very specific circumstances. So I'll let you get that written down. And so, to my two friends who showed up a little bit after I started talking, the idea here is I have 3 exams on the schedule, 2 in the middle, and then a final. That final's probably gonna be like a take-home thing, I think we're like scheduled for an 8 a.m. final or some god-awful thing like that. I prefer that. You Kyle will be ready for that, but whatever.
Kyle's like, wow.
Yeah, 8 a.m. sleeping in. Yeah, that'd be great. I'd love to give you a sleep-in day.
8 a.m. would be.
Yeah, it would. Yeah, me too. 8 a.m. would be.
I wouldn't make it.
I'd feel like I couldn't lay there that long. I'd wake up and just lay there and go, what am I doing?
Yeah, I'd be up and moving by 6:30 at the latest.
Yeah.
I wake up until 8:30 today.
I got up at 5:45 today.
Oh, wow.
Yeah, I got up at 5:30.
on up.
Yeah.
All right. What's that, Trinity?
I'm up at 9.
Hey, that's cool. You were probably up till like 2. There you go.
You would be cool.
I went to bed at 10. So,
I wish I could do that.
yeah, so the idea is to just get these things really integrated into our being so we don't have to look them up and we're aware of the existence of these results to use. So, how does this look? How do you feel about this? Does it look like you can do this? No. So again, what I would do is you can make an exam for yourself. Write a page with these things and fill in the blanks. And I might even, like on these theorems, just in case you like start them out, right? Like give you the flow and then say complete the statement or something like that. I think that can help a lot. But this sure beats doing problems under duress. Think about how long any abstract algebra problem can take. Like that one, right?
Forever.
Right, forever. So that just seems dumb to me. That's really dumb. No one is ever gonna put a gun to your head and tell you to do algebra. So, nor this either, but whatever. Somewhat artificial. So, do we wanna do this Monday or Wednesday of next week? If we do it Wednesday, I will keep cruising through stuff. Probably give you an assignment after the exam. It seems brutal and evil, but you know, that's the way it goes. Just doing school. What do we think? Do you want to have a secret vote or a conversation? Somebody toss out some feelings.
Oh, are we gonna have a homework assignment? Like we have a homework assignment starting
You will
today?
not have a homework assignment today. This is
Okay.
your homework.
Okay,
Yeah, so,
then I'm fine with Monday.
yeah? Diana, how do you feel about this?
Be honest. We're real Diana.
I'm okay. Monday seems.
Seems okay? Alright, cool. And, yeah.
Yeah, it's either, I don't care.
Alright, take that, Trinity. You sure? Okay, alright. So no homework then. And then Wednesday we'll come in and start continuing on working problems. And then I'll give you a homework assignment on Wednesday that'll be due later. Alright, cool. Great, so this is a bit of a pause, like a different, I just thought like the different thinking and energy would be, like how demented am I that I thought this was refreshing? Pretty demented. So, yeah, today we are just gonna work problems and try to be resourceful. And we will be resourceful, but it's gonna be a little bit painful. Does everybody have their book with them today? Yay, cool. Yeah. Ah! No! It's okay. We can share. Can we share? Yeah, beautiful. Sharing's good. Sharing is love.
I very badly wanted to take it out of my bag lesson.
Glad you didn't. You saved the day. Nice. Alrighty, so let's just take a look at a couple of results together. I'm not gonna write them on the board because we can read just as well. And the results I'm mostly thinking about are in this cyclic subgroup section. So, let's take a look starting at, sorry, I gotta find my notes. I've got 2 sets of notes here, one with problems I was working that we're gonna work today. Okay, yeah, so we're gonna start with corollary. Sorry. Well, hell, let's just start at Theorem 4.1. And that's on page 78. Let's go through these. And I'll probably write some stuff on the board to help us like emphasize the key things we're looking at here. So, is everybody with me? Okay, awesome. So Theorem 4.1, all these refer to cyclic things eventually. So in 4.1 we have a group G, and we have an element of that group. If A has infinite order, then two different powers of A are equal if and only if I equals J. So let's stop for a minute. What is, can you give me a group and an element that has infinite order? This is good. Well, this is the kind of way we're going to go today. So like trying to get our brains like digging into things that we already know. So I want a group G equals, you can tell me what the op is, and then some element A in G such that the order of A is infinite. Can you think of an example of such a thing? Glad we're doing this. That's how we get strong. And it's not an example. So, could G be a finite group and have an element of infinite order? Because once you've got an element of infinite order, what does that mean? Somebody tell me what that means. What does it mean? I think we need to talk about some more basic things here. Let's go pull back just a little. What does it mean for an element to have infinite order? What? Let's slow down, even go. Let's go back further. Let's like, what does this mean? Beauty. So A to the n equals E, and n is some positive integer. Oops, turn my phone volume down. Yes. So what does it mean to have infinite order?
So A to infinity equals
Yeah.
E. Those are wonderful words, but like.
They are wonderful words, but they're not quite what we're looking for. How about in Z? What is the operation implied here? Addition. Awesome. So we've got Z with addition. Can you think of a cyclic subgroup that has infinite order in G, in Z? And all you have to do is think of any subgroup except one of them. Give me a generator. Besides 0, which is just 0, and that is finite order. Give me another element. Give me an integer. Thanks. That's an integer. What does this look like, Sydney? Beautiful. That's an infinite collection. So this is the 2, 3, and right? The zip, 2, 4, blah, 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 right? Yeah. The order has to be higher than 0. So when we talk about the order here, notice here I'm saying a positive integer that gets me back to the identity. So a positive power. So the identity will always have order 1. It's really the only thing with order 1. This has infinite order because 2 to the n is never equal to, what's my identity here? 0 for all positive integers n. There's no power of it that gets me to the identity. It just keeps on going. So that's an infinite order. Yeah, okay, cool. He hobbled back to his book. So, if A has infinite order, then 2 powers of A, if I have A to the I, and I have A to the J, and I want those to be equal, that can only happen if they have the same exponent. So that's if the order of A is infinite. But we know that that can be not the same when we have a group that wraps around, like a modular group. So let's take a look at something you spent a lot of time with, Z12. Yeah. What is the order? Well, let's take a look at our elements. Let's go smaller. That's a little crazy. Let's go 6. What's the order of 1? What's our operation here? Addition. So we have plus. So the order of an element is the order of its cyclic subgroup. And what does the cyclic subgroup of 1 look like here? Sydney, you seemed pretty good at this before. I think you're still good at it. How'd you get all those multiples of 2?
I don't know, it was like, we worked on it on the homework the other day, so it was like fresh in the mind.
Yeah, intuition, right? What does it mean? Well, we better, let's study for our exam. Let's go back even further and study for our exam. So given a group G and an element in G, what is this? The cyclic subgroup generated by A. Here, let's study. Just going to use this time for open awareness. Things come and go as they may. No, you're not getting out soon, Kyle. Okay. There's no escape. 46 more minutes here. Plus. What is this? Oh, God, thank you. It's just all the powers of A. Yeah, like all of them. Just like over here, this was all the powers of 2. So this was 2 to the m, except here we don't have multiplication. So how do I write 2 to the m in an additive group? 2m, beautiful. So it was just all the multiples of 2 in an additive group. In a multiplicative group, it's going to be all the powers. Yeah, it's just this has to be familiar because you just used it on the thing I gave back. So awesome. Okay, good. So what's this? So what?
1.
Okay, 1's in there. That's 1 times 1.
0, 1, 2, 3, 4, 5. Yeah.
Thank you. 2, 3, 5, and 6. When I take 6 times 1, it actually wraps back around. Yeah. Right. So in other words, if I take 6 times 1, that's the same as 0 times 1 here. And so using multiplicative notation, wow. Whoa, what am I doing? 1 to the 0, there we go, yeah. So these two things are the same even though they have different exponents. But that's because I have a finite group. Right? So here when you have infinite things, the only way things can be there's no wraparound. There's no wraparound, the modular kind of stuff that gets 2 things can be equal if, and check out the second result.
How's it going?
So if A has finite order, what's the order of 1 here in this group? 6, thank you. It's the number of things in its cyclic subgroup. If A has finite order, let's say n, then the cyclic subgroup is, and there's the definition of it right there, right? It's like all the powers, and that E is just the 0th power, then a to the I equals a to the j if and only if n divides I minus j. And another way of saying that is that I is equal to j mod n. Those two things are equal. So right here, let's check this out. These two things were equal, and here we have n equals 6, that's our order, and I equaled 6, and j equaled 0, and sure enough, 6 is equal to 0 mod 6. So we've got that going for us, which is nice. Anybody here watched Caddyshack like way too many times? Ever once?
Yeah, I was gonna say, I don't even know what that is.
Oh my god, I'm so fucking old. Forget about it. All right, so corollary 1 is basically something I already said. That's on the next page. For any element, the order of that element is the order of its cyclic subgroup that it generates. Now, let's look at corollary 2. For any group element, a to the k equals e if and only if the order of a divides k. Does that make sense? Please take a minute and read that like multiple times. And let's think of an example from this group. Put this up here. This is corollary 2. And basically, they give us a nice summary. At the top, pick a different element. Let's just stick with this nice Z6. It's really manageable. So in Z6, what is the order of 2? Thank you. Solid. Because the cyclic subgroup generated by 2 is what?
0, 2, 4.
0, 2, 4. All the multiples of 2 with the wraparound. Beauty, yeah? Okay. So I know that 2 to some k power is the identity, which is 0, if and only if the order of 2, if and only if 3 divides k. In other words, i.e., k is a multiple of 3. And that kind of makes sense too, right? So a lot of these things, have become somewhat intuitive to us. So for example, I know that 2 to the 9th is 0. 2 to the negative 12th is 0. What about 2 to the 5th? 500 and, what about 2, oh shit, okay. What about 2 to the 511th? Is that divisible by 3?
It's a wonderful question.
It's not, Kyle, you're right. How do you do in that? You're right. So Kyle, you're right. No, because 511 is not divisible by 3 because math, that's right.
There you go.
That's right. And you can literally just write this for everything on the exam.
Because
Math, because math. That's
that
the
what-
secret. You can do that in all your math. Oh shit, I wasn't supposed to tell you that. Do not tell Cybert I told you that. It's gonna go batshit crazy.
Is 3 one of the ones where you can like add so like 5 plus 1 plus 1 is 7, and that's not divisible by
There you go. That's how you add up the digits, and if they're divisible, if they're a multiple of 3, then the number's a multiple of 3.
Huh?
So, yeah, it's great. So to determine if something is a multiple of 3, for example, that is divisible by 3 because the digits add up to 9.
So like 5 plus 1 is 7, and 7 is not divisible by
Where
3.
did we learn this?
Just like common knowledge.
Elementary school, no, it's like some weird math trick that they do.
Yeah, well now you know it, it's a super powerful trick.
I'm so glad we could be helpful to you today, Kyle.
Absolutely. I'm glad this discussion's worth something.
Yeah, just.
Well, now you
I've done
know.
a lot of mental math in my day, so I think 511 was not divisible by 3.
So you're good to go though now, right? That's a sweet thing.
Yeah.
What about this one? Let's see here, so, 9, no, that's not it. So what are we up to so far? 21, what about, oh, this is already dumb. This is just dumb, you already did there, right? Divisible by 3? Yeah. No. Divisible by 2? Even, so divisible by 2. It's an even number.
Oh, no shit.
I'm trying to trick you. Is it divisible by 6? Well, what is it? What do we know it's divisible by? 3, 2. So it's
Oh,
divisible by
yeah.
3 times
Okay.
2. 6. Yeah, exactly. Divisible by 5?
No.
Why?
5 or 0.
It doesn't end in a 5 or 0. Cool, awesome. So we know some things. There's some other weird ones. There's some weird ass ones with 7, but I can't quite remember them off the top of my head. A number is divisible by 4 if its last 3 digits are divisible by 4. So that's a good one
I
too.
didn't know that.
Yeah.
Wow.
All of this is gonna be forgotten by tomorrow.
It's okay, Kyle. It's fine.
Just remember the 3.
The 3 one gets you pretty far. Yeah, it certainly would get you here, right? So no, so this is not, because 3 does not divide the power, and 3 is the order of 2.
Okay.
All right. Okay. What's next? Oh my goodness. Is this one of the things I'm asking you to do? Oh shit, I don't even know anymore. Yeah, well, you can read this other. Theorem 4.2 is kind of what I really wanted to get to. So let's look at Theorem 4.2. I'll put the statement up here on the board. Because this is a super powerful one. This was the one the other day, Kyle, I thought was gonna help with some issue we were having, and then I was wrong.
Yeah.
But it's still useful for lots of things. So Theorem 4.2. Cyclic subgroup generated by A to the K. So again, A is an element of a group. We don't know what the order of A is here. Oh, we do. And so I have to read a little further, so imagine that. K is a positive integer. Those are good things for this. So I should be looking at the blue box, but I've got the nice summary above. So the cyclic subgroup generated by a power of A is the same as the cyclic subgroup generated by the GCD of that power and the order of that element. And then the order of that power is n over the GCD of n and k. Now we're not going to go prove that because I think it's more important for us to understand it. Today's all about understanding, not just watching proofs go by that get lost in the wind of our minds. So, let's take a look at something. Let's go to Z12. What does Z12 look like?
0 to 1.
0 through 1. Beautiful. We're all waking up. This is great. Happy morning. Quite beautiful. So this is our group G. Let's take an element out of here. What's the order of 2? 6, yeah. And the way to answer that is look at the cyclic subgroup. So it's the order of the cyclic subgroup generated by 2, and so lots of, I've seen this on the homework. I think I got a couple homeworks to get back that maybe I didn't give you too. So 0, 2, 4, 6, 8, 10, and then that's it.
That was it, yeah.
Is that right?
Yep.
Yep. Cool. So the order is 6. Quite beautiful. So now I'm going to ask myself, what is the order? Let's just do it like this. What is the order of 4? Now Now we can probably figure that out. We can see that it's 3, right? Because it's 4, 8, 12. Gets me back to 0. So there's just 3 things in there. Let's use this result. So this is actually equal to the order of 4 cyclic subgroup generated by 4, and that's equal to the cyclic subgroup generated by 2 squared. So, yeah. So this is equal to, so n is the order here. So this is equal to the order of the cyclic subgroup generated by a to the GCD of 2 and 6. Nothing terrible here. What's the GCD of 2 and 6? 2, yeah. So that doesn't tell us a whole lot. If I had picked a bigger power here, this would have been a little bit more interesting, but it's like, yeah, okay, it's just 2 squared. But I can get the order of this subgroup from this formula, and that's kind of the powerful part of this thing. So the order of 4 is the order of 2 squared, and that's the original order of 2 divided by the GCD of 2 and 6, the power and the original order. We just figured that out. That's 2, so that's 6 over 2, 3. Now all this stuff is right in front of us, so it's like, doesn't seem amazing, but imagine you had like Z240, right? That's crazy. This would make life much easier in working with these orders. So that formula is super important. That's why it's one of the things on your slate to remember. That formula right there. I'm not even going to ask you to use it yet. I mean, there'll be homeworks where you have to do it. Let's try to do another one. Let's see. Choose another one. I've got some problems I worked out last night. Shit, let's just make up one. Let's try to do something powerful and use this result. So let's take Z240. That sounds fun. Something that we can't draw out, write out all the elements of, so let's consider Z240. Definitely, it's 12 related for sure. What is going to be, now check this out, we can actually find the order of an element as well. So what is Z240, what is the order of this group? Let's just start there. 240, right? Yeah, so that's lovely and wonderful with these mod groups, these modular groups. We've got the answer to the order right in front of us. So what is a generator? Oh, actually, how about this? What is the order of 2 in this group?
120.
Yeah, 120. Right, can you imagine, because it's just half the elements of Z240. It's just the even ones. So that's 120. So this is going to be our n right now. What is the order of 16? So now we could like work out all the multiples and stuff like that. Yeah, and how'd you get that, Kyle?
So 16 is equal to 2 to the 4th.
Beautiful.
And it's so you take 120 then over the GCD of
4 and 120.
Yeah.
Yep.
Which is 4.
Which is 4.
20 divided by 4 is 3. We have 30 rather.
Lovely. Exactly. Way less painful than writing out all the multiples of 16. Bless you. Totally possible, but kind of a waste of time when we have this killer result. Okay, that's a really good result. We're going to put some of this stuff together first. I just want to go through it in a minute. how about on page 82, check out the corollary of this theorem for 2. Corollary 1, orders of elements in finite cyclic groups. So in a finite cyclic group, the order of an element divides the order of a group. We already kind of knew that, right? We've had some homework that led us to believe that, but we can prove it directly from this theorem. And so now check out corollary 2. If I have an element of order n in a group, I don't really even know what the group is. But the fact that A is n, the order of A is n, means this group G, no matter how crazy it looks, has a subgroup that I understand. I now have a subgroup in there. I have the cyclic subgroup. So that is a subgroup of G. And the order of that subgroup is the order of the element. So the minute I've got a finite element, or a finite order element, I have a subgroup. Done. So we have the order of A is n. Then A to the I equals A to the J. A to the ith power, the cyclic subgroup generated by that power, is equal to the cyclic subgroup generated by that power, if and only if the GCDs of these two numbers are the same with respect to the order of the element itself. So only if GCD with I in the order of A is equal to GCD of J in the order of A. So if they both have the greatest, if they have the same greatest common divisor with the order of the element, these two numbers up here, then we're good to go. So let's take a look up here at the Z240. So let's say in Z240, and we're going to ask this question, is the cyclic subgroup generated by A cubed the same as the cyclic subgroup generated by, oh, I got really scared. I didn't even know you had gone, and I was like, this person is showing up way late. First, let's do a little bit chiller first. Start out easy. Is this true? And I guess I should tell you what A is, right? That might help. Yeah, that would help. Yeah. So let's say that the order of how about this? Sorry. This is what I should be saying. 3 and 5. So I'm pulling back a little bit, making this a little bit more challenging. What generates all of Z240? So let's go back. Z240 is generated by what? Just give me one thing. Thank you. Yes, I was trying to be suggestive. One thing. 1. So we've got that, and the order of 1 in this group is 240 because it's the very first non-zero thing. So what power of 1 is this right here? If we were going to use multiplicative notation, this is 1 to what power? Third power. And this is 1 to what power here? Fifth power. But that just means 3 times 1 and 5 times 1 in this particular group. So, what is the GCD of 3 and 240? 3. What's the GCD of 5 and 240? 5. Thank you. Are these two subgroups equal? No, they are not. So that's a nice way to use this. Now, these are kind of lame examples because it would have been much more interesting to do something, like 124 and then some other crazy number. And if I'd prepped this, that would have been a really good thing. But, so like 80. Are those two the cyclic? Oh, that's not even fun. How about that? Let's do that. Are those two groups the same? this at 240. And I need the GCD of this at 240. I'll start doing some factorization. Hell, I'll factor 240 for us. We've done that algorithm before to find prime factorizations. Yeah, just keep dividing by primes moving up the chain. So that's 240. Here's 82. So I'll do the scratch work over here. Shit. Well, that's weird, right? Is this divisible by anybody? Nobody low, right? Not 3. We know, no, Kyle can answer that in a heartbeat. Is this divisible by 3? It is. It's 3 times 17. I already said that once in here because I just love that fact. But that is divisible by 3. But that isn't. So I think that's actually a prime number. So 82 is 2 times 41. And then 124. What can we do with that? Anybody factor that already? Oh, can you? Okay, cool. So let's see here. So this is.
Oh, no, you can't do that, that's wrong.
Oh, yeah. And then that's also a prime. So this is 2 squared times 31. So what is the GCD of, where the hell am I? Blah, 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 right down here. What is the GCD of 124, 240? 4. Looks like 4. Yeah, we agree with that? 4. What is the GCD of 82 and 240? 2. Yep. So if I doubled this, then we'd have been okay, right? So if I'd actually put 164 here, that is the same subgroup. But right now, they are not. I kind of wish I had, because that would have been cool and surprising. But does everybody see that? That these are the same subgroup. And that actually is pretty shocking. I find that somewhat shocking. And it's something that would be so painful to discern on by hand without this result. Groovy. Oh yeah, hey book. How you doing? Okay, so let's see, where were we? That was corollary 2, right? Yeah. Corollary 3 is super powerful. Tells me how to know if I have a generator of a cyclic subgroup. And that is, let's say I have some element A, where B, the eraser. So if I have an A and G, and the order of A is N, and I'm curious if some other element is a generator. So right now, A is the generator by definition. Equals the cyclic subgroup generated by A, and it's all the powers of A, and what does that look like since the order of A is N? Looks like that. Yeah. Okay, cool. So this result tells me which of these other things generate the whole subgroup. And it tells us that A to the K is a generator of this subgroup if and only if the GCD of K and the order of the subgroup is 1. So now let's take a look at something specific. So let's say we are in Z15. got Z15. Give me a generator of Z15. Give me an easy one. Let's go low hanging fruit. 1, yeah. In these additive groups, 1's always your generator. You can always pull that out. So generated by 1. What is the order of 1? 15. Thank you. Cool. We're just saying the same things over and over again. So now here's my question. Is 3 a generator? So is 3 a generator? Yeah, you're right. Oh, good Lord. Generator. Why not, Kyle?
Get out of the way here, because the GCD is not equal to 1, it's equal to 3.
Yeah, so the GCD of this element and the order of the group is 3, not 1. They can't have any common factors together, otherwise the rhythm will get you to skip with the wraparound. So no, because the GCD of 3 and the order of the group is 3, and that's not equal to 1. What about 7? It is, yeah, because, yes, because the GCD of 7 and the order of my group is 1. So instead of having to go, okay, what's 7 to the 0? What's 7 to the first? What's 7? Instead of doing all that, I just saved myself a lot of time and a lot of pain. And I've been doing something a little subtle here deliberately that I want you to notice. Working with this thing here, you're really just working with the exponents, right? So if I take this cyclic, this general cyclic subgroup, and I multiply two things together, what do I do with the exponents? You add them, right? And the order of this thing, there's the order of the subgroup is n, and so a to the n wraps me back around. There's really only one cyclic subgroup of order n, and we're gonna hit a result that says that. So there's really only one cyclic subgroup of order n. They just look different, but we can treat any one of them as z to the z mod n. So you get a cyclic subgroup of order n, it can just be thought of as this, because it's all about the exponents. It's all about the exponents in this thing. So like this thing here correlates to m. This correlates to n, and this correlates to n plus n. And this is just a modular group with addition underneath it. So it all comes back to just the exponents. So a very powerful result. Just wanted to point that out. We're gonna hit it in a minute, I think. Look at corollary 4. They're starting to make this correlation even stronger. An integer k in z mod n is a generator, if and only if the GCD of that integer and the order of the group is 1. So when I ask, got Z240, and I ask, does 7, is this equal to Z240? Does that generate the whole group? Yes. Yeah, yes. Yes, so what's the GCD? Is this thing divisible by 7? That's, you know, we have to test it, right? So we go, all right, 7 goes in 3 times, and then I've got 3 left over, and 4, and then I've got a remainder. So no. So 7 isn't a factor of this. So since the GCD of 7 and 240 is equal to 1, this is a generator of Z240. Is 3 a generator of Z240? What's the GCD? 3. There we go. So now we've got a much more powerful way to just answer these questions without enumerating horrible lists of powers and things like that. Cool. So, please turn the page for something that seems like it should be important. At the top of page 84.
Fundamental theorem of calculus.
Yeah, right? Like stuff like that always seems pretty important. Fundamental theorem of calculus, part 1 or part 2, they're both pretty vital. Everybody learns about them and then forgets them because, you know.
Oh yeah, I forgot.
Sandra asked us what the
Completely forgot.
fundamental theorem of calculus was the other day, and we all looked at each other and we were like,
So here's the question you'd ask the professor if they ever ask you that again. Say which part.
oh. I don't know either.
It's still,
I don't remember either.
Oh, well, we have to tell you, now we have to at least talk, oh no, this won't be on the test. FTC, part 1 says that if I do a definite integral from a to some variable x of f of t dt, and then I take the derivative, and so no the variables here, that's just f of x. So this is saying derivatives undo integration. Part 2 is that it's the other way around. Part 2 is that if I want to find the integral, the definite integral from a to b of f of x dx, that I take the antiderivative of f and evaluate it from a to b. This is the part 2 is the one you use the most in calculus. That shit's crazy. That to do this, and this is a Riemann sum and infinite rectangles and just beautiful, mind-blowing shit. And this is just do the antiderivative. It turns this process into algebra in a way. Calculus, the method of integration. What's that? You want a calc test?
Calculus is great.
Calculus is awesome.
It's not bad.
It's the best math class there is.
Well, you are not in it right now.
No, no, I took it a very long time ago.
Oh, the glory days.
Holy
Sorry you had to move on, Connie. So the fundamental theorem of cyclic groups. Every subgroup of a cyclic group is cyclic. There are no other kinds. So you got a cyclic group, every subgroup is a freaking cyclic group. Yeah? Sounds pretty cool. It's nice. It tells us no need to look for anything else. If the order of the cyclic subgroup generated by A is n, then the order of any subgroup is a divisor of n. Does that sound somewhat reasonable given our discussion today? Yeah. And for each positive divisor k of n, the group has exactly one subgroup, namely the subgroup generated by a to the n over k. So now let's knock this shit out. Let's put this to use with z fucking 240. So what is this result saying? It's incredibly powerful. Wildly powerful. So it says if we can factor the order of our group, we now own every single subgroup. Anything that's a factor has a corresponding subgroup. So let's take, let's go to Z24. We don't have to go to fucking Z240, as it's known in, professional circles. So we've got Z24. List all the subgroups of Z24. That means I have to factor it. So I get all the factors of Z24. There's probably one. It's a factor. One divides lots of things, most everything. What's the next one? 2. What's the next one? 3. Yep. 24. Nice. And these are paired up, right? So, how many subgroups of Z24 are there? There are 8 subgroups. And I know exactly what they are because look at the formula. The subgroups are a to the original order divided by the order of my little subgroup. So, this should have been, this is a little lame here. I kind of needed to put these around here because I'm just listing numbers otherwise. Each one of those is a cyclic subgroup. What's that? It's a little bit of a mess. Yeah, but I'm not gonna rewrite it. To use your imagination. And so what is the order of the cyclic subgroup generated by 1? Well, it's the original order of the group divided by the order of 1. What is that? 24. Oh wait, no, sorry. 24 divided by 1. Yes. So it's just 24. Cyclic subgroup generated by 2, what's its order? 12, because it's 24 over 2. It's 12. 12, whoop. Yep. And then good old, I'm just back to where I started. Oh no, I'm not. That's just like the trivial one. So this is actually just the 0, right? So this is really just the trivial subgroup. Same thing as 0. Wickedly powerful. If you look at the corollary for subgroups, that's something that's going to be on the exam. It basically just says that theorem for Z mod n. And if you understand it for Z mod n, you understand it everywhere. As long as you understand that Z mod n is really every cyclic subgroup of order n. Wicked powerful. Let's take a quick look at page 86. We're not going to work a lot of problems today. We'll save that for Wednesday. We'll come in and work a bunch of stuff together using these results in practice. So Theorem 4.4. First off, let's talk about the Euler Fee Function. Anybody know that just because you've seen it before? No? No? Cool. So it's equal to the number of integers between 1 and n minus 1 that are relatively prime to n. It's a strange function, but it's useful in a class like ours. So what is, let's make a table. Here is n, here's phi of n. Well, 1, that's kind of lame. What about 2? Up to, how many things up, so what's n? Here's n.
Yeah.
There's only one thing less than that, is 1, yeah? What about 3? Now things are starting to heat up. 2, 1 and 2, yeah? 4? 2. So yeah, so 1 and 3. Five's a prime, right? So there's only one thing it's divisible by. What's that, Kyle? You look shocked. That are relatively prime to 5. So common divisors, right? No common divisors. So we got 1, 2, 3, 4, and we're looking for common factors with 5.
Right, but we're looking for the number of integers which are relatively prime to 5, which is 1, 2, 3, and 4, right?
Oh shit, yes, thanks. I did the ask backwards thing. Yep, thank you. Sorry.
Yeah,
Thanks.
that was my
Sorry.
confusion.
Sorry. Yeah, apparently that was my confusion as well. Thanks. So let's double check. Do they actually go up to the number itself? I don't think we do, because that would be weird. Less than n, yeah, cool. Let's look at the table. Oh, table agrees, cool. So you can see the table on page 86, I don't need to fill in the rest of it, but that's where they're getting those numbers from. Really strange function. So let's just take a quick look at theorem 4.4 then. Pretty much the last result you need to, did I put corollary 4.1 as well? Can't remember. If D is a divisor of N, I did, awesome. The number of elements of order D in a cyclic group of order N is phi of D. Let's write that result up and look at it together. This tells us how many things of any particular order are in a cyclic group.
This chapter's wild.
What's that?
I said this chapter's wild.
This chapter is pretty wild.
It's just a bunch of cheat codes for what we've been doing all the time.
Yes, it is. Yes, it is. It's like every math class, right?
Yeah.
You suffer.
Yeah.
And then we make it.
You use the fundamental theorem of calculus, and then you learn the tricks.
That's right. That's exactly right. So if D is a positive divisor of N, and we'll just assume positive here, then the number of elements of order D in a cyclic subgroup of order N is phi of D. So let's go to Z24 again. We've got all our friends over there. We can maybe verify all this stuff. The number of elements of order blah. So in Z24, the number of elements of order 4. Is phi of 4. And that phi kind of depends on your ultimate order, right? So there's like a hidden, it's almost should be a phi sub n, which would kind of be nice. Oh no, yeah. Oh no, it's just phi of D. No, it's literally just phi of D. So what's phi of 4? 2. So what are the elements of order 4 in that group? So 6. So 4 is a divisor, positive divisor, elements, order D. So we definitely have 4, so we definitely got 6. There's another one. So we know that 4 is order 6. Oh wait, that's not what I mean. Order 6, 18 is 4. Yeah, I think, yes, coming in from the other side, right? Yeah, exactly. Because that's -6.
Yeah.
18 is -6, so 18, yep, equals 4.
I don't know
So
why.
finding those elements might be a little tricky. Do you see what I mean about this is just -6 in that group? As we go from 0 up to 23, and this one says move forward 4. And negative just means go to the end and move in 4. Yeah, good job. So you don't have to use these results yet. But once you get them in your heart, it's going to be a lot easier to use them. And that's the plan for Monday. We good? Yeah? And you know, honestly, if all you have to do is get the essence of the thing out, right? So like if there's little details, whatever. I want you to understand the heart of these results. That's all. Cool. So no homework, that's it. Oh, by the way, I do have some homeworks to give back and some homeworks to potentially collect from some friends. So much for you to give back. I got a snack. Here's Trinity, I got this one. Stack. Waffle food stack. Thank you. Maybe I'll erase the board today, that'd be nice. Be a chunk.
Thank you.
Yeah, thank you. Trinity, have you happened to run into Dr. Michael Bust yet or heard from him? Okay.
I tried to stop by his office hours yesterday morning, but as you know, I don't get up early.
Oh, gotcha. He probably wasn't there
He
anyway.
probably wasn't even there.
I'm
but
glad you didn't get up
When I
early.
went, he wasn't there, so.
Yeah, cause on Friday, yeah, he
Bye,
went
Dr. G.
by. Yeah, agreed.
So I'm gonna try again tomorrow, slightly earlier.
Well, I was talking to Dr. Narcissi about this, and at some point we need to just say, you know,